the pH scale and pH calculations. And this lesson, we're going to get into a little bit of the math involved with acid-base reactions. So one thing you should know is we're not going to get into all of the math. There is a ton more math, and it's some of the worst math in all of general chemistry that's just not going to be part of the high school curriculum. Now, if you take an AP course somewhere down the road or you take general chemistry in college, you will be on the hook for a little more math than you're going to see here. So, but here we're going to keep it fairly basic. So, and I don't mean like basic, but I mean simple. However, it is going to involve logarithms, and you should have a calculator handy. Now, this lesson's part of my high school chemistry playlist. I'm releasing these lessons weekly, so if you want to be notified every time I post one, subscribe to the channel and click the bell notification. All right, so I want to start with talking about this pH scale, and some people refer to this as the power of hydrogen, if you will, and it turns out it's a little bit of a mathematical definition we'll get to in a little bit. But this pH scale, it turns out it's something we can measure. We often have what's called a pH probe, which would be kind of the same shape of this marker, and you dip it into a solution, and it would, if you got a digital pH meter, give you a digital number back. And it turns out if the pH comes out to exactly 7, you've got a neutral solution. And if the pH comes out lower than 7, you've got an acidic solution. And if the pH comes out higher than 7, you've got a basic solution. And so this scale is really nice for really quickly, figuring out not only is our solution acidic or basic, but how acidic or how basic. Because the lower the pH, the more acidic it is. And the higher the pH, the more basic it is. Things of this sort. So if you look again, pure water is at a pH of like 7. Your blood is like pH 7.4. A can of Coca-Cola is at like pH of 2.5. Your stomach would be like in the range of like pH 1.5 to 2.5. Your small intestine would have a pH of like 8, a little bit basic. These sorts of things. So one thing to note about this scale is it is a logarithmic scale, and that's kind of an interesting concept here. So like if I look at pH 6 here and pH 5 here and pH 4 here, work our way down, it's a logarithmic scale. And so kind of a weird thing, like if you look at pH 7 versus pH 6, well obviously pH 6 is more acidic, but you're going to find out it's actually 10 times more acidic. Every pH unit is a power of 10 because this is a log base 10 scale. So like pH 5 compared to pH 6, pH 5 is 10 times more acidic than pH 6. And the reason we use a scale like this is that it turns out that acidity has such a huge range of possibilities. Like if you go to like pH 0 compared to pH 14, you're looking at like a range of possibilities that spans like 100 trillion, a factor of a difference of 100 trillion in acidity and stuff like this. And because that's such a broad range, that's when it's convenient to use a logarithmic scale. So another example of a logarithmic scale you're more likely to be familiar with, although you may not have known it was logarithmic, is the Richter scale for earthquakes. And it turns out it's not a log base 10 scale, but it turns out that it is logarithmic. And so like if you have an earthquake of say magnitude 5.0 on the Richter scale, if you compare that to an earthquake of magnitude 6.0, you're like, okay, it's a little bit worse. No, it's actually 31 times more powerful earthquake. It is significantly worse, if you will. And then if you go to like an earthquake of 7.0, that's 31 times more powerful than the earthquake that was at 6.0. And if you compare that earthquake at 7.0 compared to the earthquake at 5.0, it's 31 times 31, over 900 times more powerful earthquake. It is huge differences. And so same thing here. Every pH unit is a power of 10. So again, how many times more acidic is 5 than 6? 10 times more. How many times more acidic is 4 than 5? 10 times more. How many times more acidic is 4 than 6? 10 times 10, or 100 times more acidic. 10 squared more acidic. So 2 pH unit, 10 squared, 100 times more acidic. 3 pH unit difference, 10 cubed times more acidic for the lower pH value. That's kind of how that works. All right, so that's our pH scale, but let's talk about what this even means. Well, it turns out it's related to something that goes on in water. So let's say I told you I have a pure bottle of water. It's absolutely pure. It's the highest quality stuff you can buy. And then I said, okay, you want to sell me this pure water? It's absolutely pure. How much dog hair is in it? Well, hopefully 0, right? This is the most expensive, most pure water on planet Earth, right? Hopefully 0. And then if I said, well, how much, salt's in it? How much sugar's in it? Hopefully I'm getting zeros across the board. But if I said how much H3O plus is in it, hydronium's in it, how much hydroxide is in it, they could not say 0, even for the absolute the most pure water on planet Earth. And the problem is that water itself undergoes a chemical reaction within the solution where we call it autoionized. We call this the autoionization of water. So it's actually going to, two water molecules are going to react. One's going to act as an acid, one's going to act as a base. So the one that acts as an acid gives away an H plus and turns into hydroxide. The one that acts as a base accepts an H plus and turns into hydronium. And so you end up forming equal amounts of hydronium and hydroxide. And it turns out you're only going to form a tiny amount. And it turns out there's what we call an equilibrium constant associated with this, and we'll learn about these in the next chapter. So I'm just going to allude to it now. But it turns out the equilibrium constant governing this specific reaction is 1.0 times 10 to the negative 14. Now that's a really tiny number. That's 0.000 with, 13 zeros and then a 1. Super tiny number. And all that ultimately means right now is that you don't form a lot of products. That's what that being a tiny number means. You get very little of these products. And it turns out though that this number equals the molar concentration of hydronium times the molar concentration of hydroxide. And so in water, they actually always multiply together to give 1 times 10 to the negative 14. Well, in pure water, they're equal. Now, what happens if you put an acid in the water? That acid, according to Arrhenius, causes the amount of hydronium to go up. That's what acids do, right? Mr. Arrhenius said. Well, if you notice then, if all of a sudden your hydronium concentration went up, well, if these two still have to multiply to give 1 times 10 to the negative 14, that actually is going to imply that your hydroxide concentration goes down. And so an acid actually does two things. It causes the hydronium to go up, which inadvertently causes the hydroxide to also simultaneously go down. And if you add a base, it actually does the exact opposite. So if you add a base into water, Mr. Arrhenius said a base is a hydroxide donor in water. It causes the hydroxide concentration to go up. Well, again, if you cause the hydroxide concentration to go up, the hydronium concentration has to go down. That way, again, that when you multiply their concentrations together, it still gives this same constant value. All right. Well, again, in pure water, though, these two concentrations are both equal. And so if you have two numbers that are equal, multiplying to give you this guy, well, then you could kind of say x times x equals 1 times 10 to the negative 14 and take the square root, and you'd find out that these are each equal to 1 times 10 to the negative 7 molar. And it turns out your hydroxide would equal the same in pure water. And it turns out that is actually what corresponds to this pH of 7. And it turns out, we'll talk about what that pH actually means in a second. But any solution where these are not equal, but there's more H3O plus, is going to correspond to a solution with an acidic pH, lower than 7. Any solution where there's more hydroxide than hydronium is going to correspond to a basic pH higher than 7. And again, it's only when these two are actually exactly equal that you're at a pH of 7 and you have a neutral solution. Okay, so let's talk about what pH actually is. So it turns out P has a mathematical definition. Again, some people call this the power of hydrogen, but P actually means negative log. So pH is negative log of H, and technically the H plus concentration. And again, you should remember that some people write this as negative log of H3O plus because they're equivalent. But again, when this was originally derived here, they called it negative log of H plus, and that's how I'm going to write it, just so we remember that P means negative log. And then we can also talk about POH, and P again just means negative log, and negative log of whatever else you write. So POH would be negative log of OH, in this case hydroxide concentration. So these are the definitions we're coming up with here. So if you look here, like with the hydronium, which is again the same thing as H plus, being 1 times 10 to the negative 7, well, what happens if you take the negative of the log? Well, what's nice here is powers of 10 and logs are inverse functions, in the same way that like multiplication and division are inverse functions. So if I took my net worth and I doubled it, and then I took my new net worth and cut it in half, well, then I'd be right back where I started. I multiplied it by 2 and then I divided it by 2. They undid each other. They're inverse functions. In the same way, log and powers of 10 are inverse functions. And so we're going to take the negative log of this number. Well, it turns out if you take the log of this number, then you just get rid of the power of 10 and you get negative 7. But if you take the negative of that, you're going to get 7, positive 7, the negative of negative 7. And that's where that comes from. Now, again, I'm doing this, for nice powers of 10. You can do these in your head if you know how logs work and stuff like this. But pull out that handy dandy calculator, rely heavily on your calculator for this section. And again, I'm going to show you how to do these in your head, but I still recommend on a test that you use your calculator. All right, so going back to this then, if we rearrange these a little bit and solve for the H plus concentration, it's going to be 10 to the negative pH. Now it turns out I'm actually just rearranging this, and depending on your algebra skills, maybe you can see this, maybe you can't. So, but what I would do to solve for H plus here is I'd have to move the negative sign to the other side. So I'm either multiplying or dividing by -1 on both sides. It cancels over here, leaves you with negative pH over here. And then to get rid of the log, well, how do you get rid of log? Well, you use the inverse function. And as we just learned, the inverse function of log is 10 to the power of. And when you do 10 to the log, it cancels. And this side, you're just going to be left with H plus. But this side had the negative pH, right? And then you do 10 to the negative pH. And that's where H plus equals 10 to the negative pH comes from. I'm just rearranging this equation to solve for H plus. It works the same way on the next one with OH minus. It's just going to be 10 to the negative pOH. Okay. Almost there. A couple more equations. So it turns out we also remember that H plus times OH minus is going to give us that constant right up there, 1.0 times 10 to the negative 14. All right, last part of this, and this one's going to be a little easier because this is kind of a pain. This is not something you normally want to do in your head and things of that sort. But if you take the negative log of both sides of this equation and rearrange it just a little, so negative log of H plus is pH, negative log of OH minus is POH, and a property of logs makes them additive. And then negative log of 1 times 10 to the negative 14 is going to be 14. And so it turns out that pH and POH add up to 14 because of that autoionization of water constant, that 1 times 10 to the negative 14. That's where that comes from. Now, one thing to note, this autoionization constant, that is actually its value at 25 degrees Celsius. But if you change the temperature, it changes the value of that constant a little bit. And notice this constant, that's where this scale comes from, and pH 7 being neutral, and below that acidic, and above that's basic. But again, if you change the temperature, actually it changes the whole scale a little bit. It kind of sucks. But that's also why we're only ever going to give you 25 degrees Celsius temperatures. If we don't give you a temperature, you just assume it's 25 degrees Celsius. And so all of these equations, like especially these last two, are dependent on it being 25 degrees Celsius. That's the only time we're ever going to ask you to solve like for the pH and stuff like that. Now, if you take general chemistry in, college, maybe we're going to, ask, a special question just to make sure you realize that little tidbit or fact. But even then, we're still only going to ask you to do pH calculations at 25 degrees Celsius. So that's the way that's going to work. All right. Now, what you may not see so far is that if we look at these, H plus and pH and OH minus and POH, is that they are all mathematically related to each other. In fact, they're all mathematically interdependent upon one another. And what that means is that if I give you any one of these four, you could solve for the other three. So I could give you the pH, well, let's point at the right one. I can give you the pH and ask you for any one of these three. And you should be able to solve it using the equations we have right here. And that's something you want to get good at. So you want to get good at two things then. Realizing one, that if you know any one of these, there's three other things you should be able to calculate. And then also then how to calculate them. But a lot of students don't even remember that, oh, if I know one, I know the other three. They forget even that part. So you want to recognize, you know any one of these, you can calculate the other three, and then also obviously how to do so. And we've got a lovely table on your study guide that we're going to fill in one of these in every case and go ahead and solve the other three. All right, so this is what the chart on the study guide looks like here that I've replicated up here. And in each of these four cases, I've given you one of the four quantities, and we're going to use them to solve for the other three. So in the first case, I've told you that the H plus concentration is 1 times 10 to the negative 7 molar, and you might recall that that corresponds to the neutral conditions. And if you take the negative log of this, so again, negative log of the H plus gets you your pH. And negative log of this, again, the log is just negative 7. The negative of that would be positive 7. And once you got the pH or POH, I highly recommend this guy here to help you get the other one, because they just add up to 14. And in this case, 14 minus 7 tells you the POH is also 7. And then your hydroxide concentration. So if you go back and solve for that, your hydroxide's 10 to the negative of whatever the POH was. So in this case, 10 to the negative 7. And so in this case, we'll write 10 to the negative 7 molar. And keep in mind that 10 to the negative 7 is the same thing as 1 times 10 to the negative 7, because anything times 1 is itself. Now, if we had 2 times 10 to the minus 7, or 3, or 4, or 5, or anything times 10 to the negative 7, that's not the same thing as just plain old 10 to the negative 7. Keep that in mind. All right, but again, we only knew the first. That was the only one given. We figured out the other 3. Let's move on to this again. So here I've got the pH, and if you know the pH, easiest thing to get next is the POH. And since they add up to 14, well then 14 minus 3 gets me a POH of 11. And then if I want to get the H+, the H+ is just 10 to the negative of whatever the pH is, so 10 to the negative 3. So this will be 10 to the negative 3 molar, which again is the same thing as 1 times 10 to the negative 3 molar. Same thing here, your POH is 11, and so your hydroxide is 10 to the negative 11, which is the same thing as 1 times 10 to the negative 11. All right, so these 2 rows weren't bad. They were nice whole number pHs. That's not going to be the case for these last 2. And so these you might get to a point where you feel comfortable even doing them in your head. You're probably never going to get there with things like this, truth be told. And this is where we definitely want to rely on our calculator here. So in this case, we're given the hydroxide, and there's nothing that I can really figure out too easily in my head, which is why we just pick up that calculator. And so to go from OH to POH, I just need to take the negative log of the OH. So I'm going to take the negative log of that number. So negative sign log of 3.2 times 10 to the negative 11, and I'm going to get 10.5. Okay, and now that I've got a POH, I have a quick way to get the pH, because they add up to 14. And 14 minus 10.5 gets me a pH of 3.5. And then finally, your H+ concentration is 10 to the negative, whatever the pH is. And so in this case, 10 to the negative 3.5 molar. Right? What's wrong with that? Yeah, you can't put decimals in your exponents for proper mathematical notation. That doesn't work. And so in this case, that doesn't work. If you had a multiple choice test and they asked you for the H+ concentration, that ain't going to be how it's written. And so this is when you use your calculator. And I'm just simply going to take 10 raised to the power of, so I'm using my caret button, negative 3.5, and I get 3.2 times 10 to the negative 4. And so if I'm using my chicken scratch and just, calculating it out, great. Write it however you want to. But if you're looking for the actual formal answer, it ain't going to be written like this. And so we'll go back. And again, that was 3.2 times 10 to the negative 4 molar. All right. Finally, last one. We've got a POH of 2.5. And once again, if you've got a pH or a POH, highly recommend you just go and get the other one pretty quickly. And so 14 minus 2.5 should get us 11.5. All right, and then once again, we have this issue where 10 to the negative 11.5 or 10 to the negative 2.5 is not properly written, but we'll just plug those into our calculator to get us a better answer. So in this case, 10 to the negative 2.5, 10 caret negative 2.5 is going to get us 3.2 times 10 to the negative 3. All right. And then we can do 10 to the negative 11.5 same way. Now, one thing to note, I personally just don't like multiplying. And the truth is, once I've got the OH concentration, I could use the fact that these multiply to give 1 times 10 minus 14. So I could take 1 times 10 to the negative 14 and divide it by the 3.2 times 10 to the negative 3 to get the H+. I could. I just don't like calculating that way, and there's another way to do it. And I'd rather just do 10 to the negative 11.5 here. So 10 caret negative 11.5, and we get 3.2 times 10 to the negative 12. Molar. Cool. And now we've kind of filled out the entire chart. And again, something that takes a little bit of practice, something you want to get good at, something you want to keep a calculator handy for, but definitely know how to use your calculator depending on whatever model you've got as well. Super important. So now we want to conclude this lesson by finding the pH of strong acids and strong bases. And with strong acids and strong bases, we know they dissociate completely, and that's going to allow us to figure out how much H plus in the case of an acid or how much OH minus in the case of a base is in the solution. Now, for a weak acid or a weak base, which only dissociate to a small extent, less than 5%, we will not be able to do such a calculation yet. But in the next chapter on equilibrium, we'll learn how. So, but for now, we're going to deal with just strong acids and bases. All right, so in In this case, we've got 0.010 molar HCl, and being a strong acid, when it dissociates, it's going to dissociate completely to give H plus and Cl minus. And since it dissociates completely, you're going to end up with an OH, not OH. You're going to end up with an H plus concentration of 0.010 molar. And then the pH, to get that, you just take the negative log of the H plus. And so in this case, negative log of that, well, it turns out 0.01 is the same thing as 10 to the negative 2, if you know your powers of 10. And taking the negative log of that is just going to get me a pH of 2. And so again, if you have nice round numbers, some of this you can actually do in your head if you want to. But again, I highly recommend relying on that calculator as much as you desire to. All right, H2SO4 on the other hand, you should remember something special about him. He's got two H's, but only the first one dissociates completely. And so 0.1 molar H2SO4 is still going to have an H plus concentration of roughly, don't need a bracket there, roughly 0.1 molar. Now it's not going to be exact because it turns out once the first one dissociates completely, the second one dissociates just to a teeny tiny extent. And so the truth is the H plus concentration won't be exactly 0.1, it'll be just a smidgen higher, but nothing we're ever going to have to calculate exactly. It's just a smidgen higher, and it's so insignificant though that we can just round it to 0.1. All right, if we then go to get the pH, we'll just take the negative log of that. And once again, if you know your powers of 10, that's the same thing as 10 to the negative 1 molar. And so the pH is just going to come out to 1. Again, will it come out to exactly 1? No, it won't come out to exactly 1 to be approximate. Now, if you did try to figure this out exactly, and you don't have the tools to do it just yet, but in the next chapter you might, but it's nothing, we're not even going to ask you this in the next chapter though, but if you did, the pH would end up coming out to like 0.99. And so the idea is that because the H plus ends up a little higher, with a great, a little more acid in there, the pH ends up a little bit lower. And you should realize there's this inverse relationship because P means negative log, then as H plus goes up, pH goes down. And again, technically this wouldn't be a pH of 1, it would be like 0.99. So, but it would be very close to 1. All right, moving on to strong bases. Now, strong bases put hydroxide into the solution instead of H plus. And so what we're going to do is calculate how much hydroxide they stick in, calculate the POH, and then subtract from 14 to get the pH. So one extra step in the calculation for a base here. All right, in the case of 0.01 molar sodium hydroxide dissociates completely to give you a hydroxide concentration of simply 0.010 molar. And then we'll find the POH. And in this case, again, that's the same thing as 10 to the negative 2, and you take the negative log of that, and the POH comes out to 2, but we're not done. Typically, you're trying to find this on a pH scale. Now, if they asked for the POH, and they could, it would be 2. You'd be done. But most of the time, they're going to be asking you for a pH, and so you got to subtract from 14 and get a pH of 12. Now, the one thing that's tricky, and we hinted at this back earlier in the last lesson with barium hydroxide, strontium hydroxide, calcium hydroxide, magnesium hydroxide, where they have two H's, and where with H2SO4, both H's don't dissociate completely. But with these, both OH's dissociate completely. And so in this case, your hydroxide concentration is not going to simply equal 0.01 molar. It's going to equal 0.01 molar times 2 for the two hydroxides that get produced. And so in this case, it actually is going to equal 0.2 molar instead. And so when you go to do your POH calculation, so you're not doing the negative log of 0.1, you're doing the negative log of 0.2. And that's not a nice round power of 10, which means we can't really do this in our head very easily. So we'll just do negative log of 0.2, and we're going to get 0.7. So 0.7. And then if we want to find the pH, we'll just subtract from 14 and get 13.3. Cool. This is how we find the pH again of strong acids, strong bases. And again, for weak acids and bases, we'll learn how to do those in the next chapter, not on the Hook forum in this chapter. Now, if you have found this lesson helpful, would you consider giving me a like and a share? A couple of the more helpful things you can do to make sure other students get to see this lesson as well. If you're looking for the study guide that goes with this lesson, if you are looking for plenty of practice problems, check out my premium course on chadsprep.com. A free trial is available.